continuing the series on Einstein's field equations. We are back with yet another episode. I call this episode 5.1 because I have to divide this episode in two sub-episodes. So in this episode, as you are viewing on the screen, that we will be looking towards three distinct components of Einstein's field equations: the Ricci curvature tensor, the Ricci scalar, and the stress energy momentum tensor. Well, before I begin this video, I should offer my thanks and gratitude to all these subscribers who had viewed my video and they have put wonderful comments on the comment section. I am especially thankful to Randy Martin, who has enjoyed this video, and he has put upon a suggestion that I should lower the background sound so that the explanations come much more vivid. So Randy, I am back with this new video, and I have listened to what you have suggested, and I hope this time the quality of the sound is better and you can listen to it more clearly. Warm welcome and thanks to Twinkle Pal, who has really enjoyed the video, Cosmo Philosophy and Science, who has been appreciating, and to Prabal, who has offered me thanks. So a big thank you to all those who have been listening and putting wonderful comments. Well, in this part we would be looking forward for the components of Einstein's field equations. As you can see right on the top of the screen, this is the entire Einstein field equations. So we would be looking towards what is called R mu nu, which is called the Richie curvature tensor. We would have a look onto that. Then there is R, the single R, which denotes the Ricci curvature scalar. We have G mu nu, which is the metric tensor. We have the lambda sign, which denotes the cosmological constant. We also have the capital G, which is the good old Newton's gravitational constant. We have C, which is the speed of light. We are all aware about that. And we have T mu nu, which is the stress energy momentum tensor. Together, all these components make up the Einstein field equations. So we would go forward one by one, step by step, and look into a detailed explanation of what those components actually mean. However, the scope of this video will be particularly R mu nu, that is the Ricci curvature tensor, the single capital R, which is the Ricci curvature scalar, and T mu nu, which deals with the stress energy momentum tensor. First, we need to know that what is this sign mu nu denote? Well, as you see that we often use Greek alphabet to denote something in physics or mathematics. Here, mu nu denotes space-time in 4 dimensions. So as you can see on the screen, the first 0 or naught denotes time, 1 denotes the x-axis, 2 the y-axis, and 3 the z-axis. So once you understand what is mu nu, which has been there in the Einstein field equation, these are the 4 ways in denoting the 4 dimension of space-time. If I plot it into an x and y axis, where t denotes this time and x, y, and z denotes the spatial dimension, then this would be time and this would be space. So this is the entire definition of mu nu, which is the time and the 3 other spatial axes denoted from 1 to 3 and the 0 denoting the time. Well, we need to understand one more thing, is that Einstein's field equations, the R mu nu actually contains 4, G mu nu another 4, and again there's a repetition of G mu nu, so taken 4, and T mu nu, which is the stress energy momentum tensor, contains 4. So all these 4 are basically, as I have shown, from 0 to 3 are the time and the spatial components. So taken together, this leads to 16 partial differential equations. But note that 6 equations are duplicate, which makes them a total of 10 nonlinear partial differential equations. So all these 4 makes up 16 equations. So that is why I always call them Einstein's field equations and not equation, because internally there are 16 equations. Deduct 6 of them, we get 10 nonlinear PDEs. Now I think you are all aware about the basic linear algebra which we have done in our school days, and we know what is a symmetric matrix. So you see here on your screen the red one, 1, 2, 3, which is on the row part, and if you transpose it you get the same thing on the vertical part. So this is an ideal definition of what is a symmetric matrix. Given what is there in the row and you transpose it, you get the same in the vertical as well as in the row. So this is symmetric matrix. Why, you are wondering why suddenly I'm speaking about symmetric matrix, but things will become clear as we proceed with the video. Now you need to understand that metric tensor is actually a symmetric tensor. The metric tensor looks like this. It is a 4x4 starting from G00 and it goes up to G33. It is a symmetric matrix, but you have to find one interesting feature of this symmetric tensor. This G01 and G10 are symmetric, so they denote the same values. G02 as well as G20 again is the same, and G03 and G30 is always the same. So what happens is that if we go on eliminating G01, which equals to G10, G02 which equals G20, and G03 which equals G30, we actually deduct all those, and what we get is a symmetric tensor. That means G mu nu equals to G nu mu. So I have shown this in your screen that we can continue reducing those which are symmetric, and this comes to the metric tensor turns out to be a symmetric tensor. So when we reduce the 10 components of the metric tensor, it looks something like this. So you see 4 plus 3 plus 2 plus 1. This makes a 10 components metric tensor. So we have already deducted 6 components and it leads to 10 components. Another important feature is that you will see all the components of this metric tensor are unique. That means there is no repetition. G00, 01 as well as 2223 and 33, they are not equal to each other, so they are all unique. So this leads to the 10 components. 16 minus 6 leads to 10 components. The 2 mu nu is also a symmetric tensor, which we call is a stress energy momentum tensor. So this is the entire 16 components of the stress energy momentum tensor. Again 01 and 10 we can deduct it, 02 and 20 as well as 03 and 30. In this way, if we continue, which I have shown at the bottom of the screen, 0110, 0220, 0330, then it becomes a symmetric tensor. So T mu nu also becomes equal to T nu mu. The 10 components of the stress energy momentum tensor, as it is displayed on the left hand side of your screen, are again similar to the metric tensor, and all the components are unique, which leads to these 10 components. So you see on the top you see 4 and 3 and 2 and 1. So this actually reduces our task in order of computation, both for metric tensor as well as for stress energy momentum tensor. We can deduct, we can cancel off those terms which are symmetric, and hence it reduces to 10 components. Okay, so what we can do is that we can summarize the Einstein's field equations. So here is the entire Einstein field equation. Now this part which I have marked in red, this is r mu nu minus half, this entire part. This can be actually shows the curvature of space-time as determined by the metric G. So G actually denotes the metric tensor. So this red part actually shows the curvature of space-time, And how do we do? Well, that is what we are learning, but it is determined by the metric G, and this is actually the geometry of space-time. The right hand side, which I marked in curved in blue, is basically the matter energy content of space-time, this 8 pi g, especially the t mu nu, which we will see in this video, that how it leads to the matter part of the equation. And this actually shows the matter movement, and you see at the bottom of your screen, geometry of space-time and matter movement are equal. So this is how we can summarize the Einstein field equation. The left hand side, determined by the metric, is actually the geometry of space-time, whereas the right hand side is the matter energy content of space-time, and it shows the matter movement, which is equated by an equal to sign. Now we can write the Einstein field equation in a different way, and this is the original form of the equation, and you see this r mu nu minus half r g mu nu. This is actually can be written as G, capital G mu nu. Now once we write this, we can replace this r mu nu minus half r g mu nu, which is the G mu nu part, plus the lambda of G mu nu equals to kappa term. There's a kappa term followed by the stressenergymomentumtensor, that is T mu nu. So this part, as you see, I have mentioned it in blue arrow. So this actually leads to the third equation on the left hand side of your screen. Now if I consider this part, the 8 pi g part, this is actually the kappa term. Okay, this is the entire I would say the equation 8 pi g whole divided by C4, and it is more or less equivalent to 2.00 and the entire term which you are seeing. Now this is actually the Einstein's gravitational constant. Okay, so we would deal with this on the later part, but just understand that this 8 pi g whole divided by C4 is a factor, is just a constant that's set so that we can recover the Newton's law of gravity for small and static masses. Now one thing what I would like to tell you is that this C4 part, which we would later deal in another video, is basically taken for the dimensional part, because we deal with 4 dimensions, so we write this C4. The pi part actually comes because we are calculating, Einstein calculated it on a spherical mass, so obviously the pi factor will come. So this is another way of writing the equation. So this part, the kappa is 8 pi g, which is Einstein's gravitational constant, and this can be written again as G mu nu, which actually will be it will be much clearer in the second part, and this comes to this one. So Einstein's tensor is defined as G mu nu, which I have shown in the just before this. G mu nu is basically the Einstein tensor. Okay, so Einstein's tensor is symmetric. Okay, and that is why we can write G mu nu equals to G nu mu, and it is representing the space-time curvature tensor. This actually tells you due to the matter distribution through the space-time in fabric. In fact, the so-called gravity force is nothing but the curvature which let matter move. So our 8 pi g we have seen is a constant. The g by c4 is required for dimensional reasons. The factor 4 pi comes from the integration over a sphere while integrating the gravitational potential into a force. We have to note that Einstein tensor is actually have zero divergence. Now we are all aware about what actually is a divergence. So zero divergence means that the amount of fluid, say for example, if you consider the fluid flow, the amount of fluid which is flowing in is the same as the amount which is flowing out. So I have just given a partial differential part of what is a divergence, which is zero. G mu nu is actually provides curvature of space-time. T mu nu as it presence of energy and mass. Now you see here G mu nu plus lambda G mu nu equals to kappa term of T mu nu. Now because T mu nu, as we have seen earlier, has a zero divergence in order to match the law of conservation, that is why you see on the left hand side with the blue arrow down, G mu nu has to have a zero divergence. So, well, the zero divergence of the stress tensor comes from the requirement of the conservation of matter and energy. It follows that the left hand side, which is the Einstein tensor, also must have a zero divergence. So because this red T mu nu, which is on the right hand side of the screen, has a zero divergence, so the Einstein tensor also must have a zero divergence because it has to balance. The books needs to balance. The covariant derivative, well, if you're wondering what is a covariant derivative, well, yes, I will make a video on what is a covariant derivative. The covariant derivative of Einstein tensor is set to 0 due to its connection with the stress tensor, and it is something like this. So here you can see there is a gamma term, which is a coefficient connection, which is used for the metric. So we can also say in this way that Einstein tensor is a zero divergence, that is assuring the energy conservation of matter. Well, Newton's law of motion can be expressed of the vanishing of the divergence of the stress tensor. When we move from the flat space to the curved one, we replace the derivative, which is this one d, with a covariant derivative. Hence the geometry produced by energy momentum tensor on one side, it must have a vanishing divergence. Okay, so let us summarize what we have learned till now. So the vanishing of the divergence of the Einstein's tensor is the same as vanishing of divergence of the energy momentum tensor, so that the left hand side, right hand side balances. The physical reason for vanishing of the divergence is the energy conservation, or its most natural way of generalizing curved space-time. Also, the Einstein tensor, as you see, it helps to write the field equation in a much compact and easier manner. Another important point is that this can be regarded also as a consequence of the fact that the theory must be independent of the choice of coordinates. We must not forget that we are dealing with general theory of relativity, which is general and independent of any choice of the coordinates. So we can summarize from here that Einstein's tensor should be equal to the stress energy momentum tensor. So the stress energy momentum tensor's divergence, zero divergence, equates with the Einstein's tensor's zero divergence. Now we have already seen that on the right hand side what we deal with is a stress energy momentum tensor. So obviously it deals with curvature, and as we have seen earlier, that curvature is equal to matter. So the question arises that what is matter? Well, you must say mass. Now moving from the Newtonian concept of mass to special theory of relativity, that mass is not simply a mass, we have a relativistic mass which is given by this. So the presence of matter curves space-time. So what consists of matter? So this is what is the relativistic mass, and the total energy of a moving body is given by this. So we need you understand a whole lot of information and catalog in order to give an information which contains a lot of things. So what does it contain? It contains energy, density, momentum, flow of energy, pressure, and as well as stress. So all these things should be catalogued in such a way so that if we are trying to point out the movement of mass, we should be able to get all those things. So the energy momentum tensor in physics actually describes the local distribution of mass, momentum, and energy. For example, in two dimensions, dimension, which is t and x, we get a kind of a matrix like this, or we can consider this to be a tensor. So these four components consist of energy density, which is red, t sub dt marked in red, momentum density, which is marked in there, and the pressure, which is marked in green. So ttx and t sub xt is the momentum density, and t sub xx is the pressure density. This, you should understand, is something which contains energy, momentum and pressure in two dimensions. Now what if we expand this fully? It leads to something like this. This is a 4x4 matrix, or a tensor, which we call specifically, and this is actually what is a stress energy momentum tensor when this component is expanded in 4 dimensions. Note that on the top right hand side there are 4 parts. One is t, x, y and z. So as we have shown earlier, this is a 4x4 matrix. So x, y and z are the 3 dimensions of 3 spatial dimensions, and t being the time. So now you can see that the 2 dimension gets expanded to 4 dimension. So this, as I have been telling, is actually the stress energy momentum tensor. Now again, you see I have considered the tensor in 2 dimensions. So if I consider the ttx, which I mentioned in purple, and txt is actually the momentum density. Don't worry, we will be soon explaining the terms, what we mean by momentum density. So now you see this term gets expanded, the momentum density in 3 dimensions, how it looks. So you have 3 dimensions, x, y and z, which are the spatial dimensions. On the row and both on the horizontal and vertical side, all this ttx and txt gets expanded into a 3x3 matrix, or you can say it gets further complex into this kind of a tensor. So this 2 dimension, which you can see right, the txx actually mentions about the pressure component of the stress energy momentum tensor. On the right hand side of your screen, you see that this txx further gets expanded into 3 dimensions, txx, tyy and tzz. Note that on the right hand side top, I have mentioned the coordinates also as x, y and z. So all these the stress component again gets expanded into the 3 components, and this is how you see I have written this as pressure. So the pressure component, the momentum density, everything is getting expanded into further 3 dimensions, and few other components which you see on the bottom of your screen, tzx, tyx, tzy. All this actually makes a 4x4 tensor, which is the stress energy momentum tensor. So this part I just wanted to show you that how the momentum density and pressure in 2 dimensions get expanded into 3 dimensions. So the stress energy momentum tensor, historically, although it is a mouthful word which looks like stress energy momentum tensor, historically it is the relativistic extension of the same classical stress tensor which we learned and dealt with Newtonian mechanics. So this is the stress energy momentum tensor. So obviously it is an extension of the classical tensor. It is a relativistic extension. It describes energy and momentum flux. This is important through space-time, and this particular tensor or this particular element gives rise to the gravitational field in General Theory of Relativity. Now this space-time for vector is defined as this Ct, which I think this is something which you already know in special theory of relativity. If you haven't, you can just check out your notes and what is a space-time for vector means. So you can see x, y, z and Ct. The energy momentum for vector is defined as this E px. We will deal with this in the next slide when once we explain this. So just trying to understand one thing, that stress energy momentum tensor is nothing more than what we learned in the classical relativistic world. This is the Newtonian tensor, which is further explained to relativistic tensor, and now we are dealing with general relativity, which is further expanded to stress energy momentum tensor. So now you see this part, I have explained it part by part. The E denotes energy, which is E equal to mc squared as per Einstein's formulation. This part deals with momentum in x direction. This is momentum in y direction, and this is the momentum in z direction. But yes, this is just a vector. We can write it in a matrix. This is just a vector, but what we are looking forward is a tensor. So from a vector, we need to move into a tensor. This won't work out, what you see right on the screen. Yes, so here it is, the entire stress energy momentum tensor. Now, the upper left component, T00, is the energy density. So if you are taking stress energy tensor as the source of gravitation and field as this one, E equals to mc squared, then always the energy density will be dominant, because the magnitude of C is much, much larger, right? And that is very high, hence energy density will always dominate the other components. You can see I have mentioned the energy flux, the pressure, which is marked in gray, and the shear stress, which is marked in yellow. Now, what you need to understand over here is that every part of the energy that we think, especially in physics, every part of the energy has been formulated, and it finds some way or the other in this tensor. So it can be anything like a pure energy, relativistic energy, rest mass, stress, shear stress, anything. Anything that we think of an energy will definitely find its part in the stress energy momentum tensor. Note that the energy density will always be bigger, and it will always dominate the tensor part, because energy equals to mass times the speed of light, and because the magnitude of C is much higher. So let us see what are the meaning of the terms. Energy density is actually the amount of energy stored in a given system, or you can call a region, especially in a system, which is per unit volume. It therefore has length of energy per length cubed. Energy flux is something you can imagine that you're sitting beside a window and the sunlight is flowing in. So that is what is called the energy flux, is the rate of transfer of energy to a surface. Momentum density is the momentum per unit volume given of any field. On the right hand side in blue box, I have mentioned this momentum density just as an electromagnetic wave. Pressure, we all know, is given by this formula, and shear stress, obviously denoted by the Greek letter tau, is basically the force applied divided by the cross-sectional area, which is mentioned in m squared. So just to make you understand that when we would be speaking of those terms, what actually those terms mean. So I have just given a basic overview, basic idea on the definition of these terms. Now here you see on the right hand side in blue, I have mentioned the stress energy momentum tensor. So we will deal first with what is called the energy density. It is the energy that is responsible for the curvature of space-time. Now as matter equals energy, hence energy is responsible for space-time curvature. When matter moves from one place to another, there is a flow of energy. The space-time curvature is thus determined by the energy density. The pressure also acts as a source which causes a space-time curvature. As you see, I have mentioned an icon where a hand is crushing an object. So pressure can deform objects and hence responsible for curvature. If I press anything too hard, I can deform the object. Hence pressure also acts towards the curvature. Okay, so next we deal with energy flux. So you understand a flux, as I have told, is a flow of something per unit time. So movement of matter causes energy to transport or transfer from one position to another. This flow of energy causes energy flux, and obviously it causes curvature. So you understand the stress energy momentum tensor, energy density, pressure, and energy flux. All of them are actually making the curvature of space-time. Each one, energy, which is equals to matter, right, mass, then comes the pressure, pressing that it would cause a curvature, and the movement of matter, which causes energy flux. And because matter causes curvature in space-time, so energy flux also causes curvature in space-time. We are left with momentum density. I have just given a basic equation from the liquid flow, that momentum flow equals to mass flow times momentum or mass. So energy and momentum are closely related. So that is why it gives rise to the space-time curvature. So when gravity is non-negligible, the divergence of the stress energy momentum vanishes. Now, here you see the energy and the momentum and the pressure and the stress all together taken contributes towards the curvature of space-time. So the right hand side, on the left hand side of the screen, you have seen that I have marked it in red so that you can understand energy and momentum. All the units of the stress energy momentum tensor is actually the presence of matter, and it is matter which is causing the dent or the curvature of space-time. So you see the energy, the momentum, the pressure, and the stress makes up the T mu nu component, which actually has a zero divergence. So when gravity is non-negligible, the divergence of the stress energy tensor vanishes. In the coordinate-free system, we generally use a covariant derivative. So this is what is covariant derivative. If you are not mathematically that inclined, what you can do is that you can skip this part. Say div T is actually the divergence of the stress energy momentum tensor. It is not energy, not mass. It is the source of the gravity, this one. Now, obviously it gives rise to a question, that is zero divergence of stress energy momentum tensor same as conservation of energy? Because I have been telling that zero divergence causes the books to balance, that is the left and the right hand side balances. So obviously the question would be, is zero divergence of stress energy leads to the conservation of energy? Well, it is no. The answer is straight away no. The reason for it is that the covariant divergence involved implies that vanishing divergence in one coordinate frame implies vanishing in all coordinate system. The stress energy momentum tensor represents energy momentum of matter. So to show, the energy momentum conservation, we have to include the energy momentum of the gravitational field, and then we can conserve the divergence of the ordinary field. So maybe this requires a little bit of attention, okay, because this is outside the scope of this video. But you need to understand one thing, is that zero divergence of the momentum tensor does not mean that it is the conservation of energy. Ordinary divergence, which we call, doesn't vanish. Only what vanishes is the covariant divergence. So that is the reason, in order to show that the energy momentum conservation is met with, we have to include the energy momentum of the general gravitational field, and then we conserve divergence. Just to put you in another note, in the Yang-Mills change coordination, it is the same thing. So when you have to take into account the Gauge-Boson change charges, and then show the ordinary divergence, and then you can combine matter, and then the field amount vanishes. So just to remember that it is not that zero divergence means that the conservation of energy. It is only when you are able to make the ordinary divergence vanish, then only it will be vanishing in all the coordinate system. So again, before we end this stress energy momentum tensor part, here is the quadrant. You can see energy density, which we have already dealt, and it rules the entire tensor because of the velocity of light. Energy flux, which we know is basically the of matter through space-time, momentum density, which we have already dealt with it, and the stress tensor, which includes pressure and shear stress. So all these components contributes towards making up the stressenergymomentumtensor, which in return makes a curvature in the space-time. So time to take a break, so you can just enjoy with a cup of coffee and a donut, and I will just go and grab a cup of coffee for me. And I can tell you this much, that topologically a person cannot make a difference between this dancing cup of coffee and the donut that is waiting on your plate. So just to take a break before we come down for the next part of the video. Okay, so welcome back to the final part of the video, where we would be extensively dealing with Richie curvature tensor. Okay, before we go ahead and move into Richie curvature tensor, we need to understand what is a Riemann curvature tensor. Well, those who are not aware about deriving or what a Riemann curvature tensor is, you can just omit what is written right below the cube. This is actually the Riemann curvature tensor, which is built using the covariant derivatives. So the Riemann curvature tensor, actually Riemann, as I called, is the granddaddy. From him actually all this tensor analysis started. It leads to the Ricci curvature tensor. So this particular part is actually making you aware about the way in which we are arriving. So Riemann curvature tensor leads to Ricci curvature tensor. Ricci curvature tensor is actually a symmetric tensor. This leads to the Ricci scalar, which I have mentioned as a summation, and it is denoted by Rii. Now Ricci's scalar is actually contraction of the Ricci tensor, which I will definitely show you in this video, again, which is in turn a contraction of the Riemann curvature tensor. So this is the flow. So Ricci scalar is a contraction of the Ricci tensor. The Ricci tensor right on the top of your screen is actually the contraction of Riemann curvature tensor. So it is basically an entire part of the contraction that we generally deal with. So just to tell you what actually in a very layman's language Ricci curvature means, actually Ricci curvature tensor gives a quantified description. I will again repeat, it gives you a quantified description of how curved space-time is. However, you need to understand that they don't provide a complete picture. For this, you need to know what I showed right at the beginning is the Riemann curvature tensor. I would be explaining on the Riemann curvature tensor in details later. The Ricci curvature scalar represents the amount by which the volume of a geodesic ball in a curved Riemannian manifold deviates from that of a standard ball in Euclidean space. All these terms will come clear as we move ahead. So this is how, just to show the entire hierarchy of Riemann to Ricci, Ricci to Ricci scalar, and then going back, these are basically contraction of the indices. So Ricci curvature actually tracks the volume change along geodesics, which means how volume grow and shrink in geodesics. Depending on the curvature, Ricci curvature, which is denoted by R, shows the change in volume in either of the following way. What are the ways? It can be static, it can be growing, or it can be decreasing. So Ricci curvature actually shows, or it tracks the volume change along the geodesics. So actually, what do we mean by volume change? We have to take a step back and we will just have a quick glimpse on what I'm trying to explain before we move into the actual part of the Ricci curvature tensor. So let us get a quick idea on what we mean by change of volume under linear transformation in orthogonal and non-orthogonal plane, that is, which is 90 degrees and which is non-90 degrees. This is just a kind of a quick recap so that we can understand Ricci curvature tensor in a much more better way. We we are all aware when in our school days what we have done that we used to use determinant to calculate the area of a parallelogram. So for example, this is a parallelogram W and V, and the area of a parallelogram in R2, that is in 2 dimensions, can be taken by this determinant. So if P a parallelogram, then V and W are vector, then we get the value of this by doing in this way. So plus minus is actually the change, and this is how we get the area of the parallelogram. So what do we mean by volume growth? Now if I take a linear transformation of Trn to Trm, where we are mapping the n-dimensional space to the m-dimensional space, so in a one-dimensional linear transformation, if you take a figure like this, so this is an example of a one-dimensional linear transformation. So you can see Tx equals to T function of x equal to 3x. So we can visualize this function on a graph which is right in front of you, and this x prime equals to Tx maps the number of x to the new number Tx or x prime x. Now, for example, so this is how it shows. The determinant of the matrix associated with T is 3, which means that T stretches. It stretches the object so that the length increases by a factor of 3, which is shown here on the right hand side, which is the x prime coordinate. Now, in a two-dimensional linear transformation, say for example, if I consider the mapping of, say for example, this one, the matrix A, B, C, D followed by X, Y. So this can be showed something like this, right? So you can see that this part, the I would say the determinant actually the sub X and Y, the entire object rotates by pi radians, and it stretches to increase to a factor of 4. Right, so here T maps the square into a parallelogram, it rotates also. So this is a stretching in two-dimensional linear transformation. So if we stretch and flip further in a two-dimensional linear transformation, this is what happens. So so the double of the area of orientation is reversed. The most important factor is the determinant of T. Yes, so here it is. The T doubles the area, and the orientation is also reversed. So you can see the blue mark going in this way, the yellow turning in this way. So it actually gets reversed. So this T actually maps it into a parallelogram. T doubles the area, orientation is reversed. The most important factor is the determinant tells how T changes area and whether it is reversed or the orientation remains. So now let us look forward. What we mean is a 3D linear transformation. So this is the equation which I have plotted in a matrix of A11 to A13. You can see that T maps into A11x, A12y, and so on, which leads to AX. So here on the XYZ graph, you can see this is a cube which has these colors. Now, this is what happens. So this actually, the determinant it increases to a factor of 12, right? So since the determinant of A equals to 12, the linear transformation of Tx equals to Ax expands the volume of the object by a factor of 12. So here you see I have written on the right hand side, the expansion of volume by T is reflected by the fact that the determinant of A is 12. T rotated the cube and stretched into a parallelepiped, which is right on the right hand side screen, which I have marked in purple, it is a volume of 12. So here what happens, the volume expands to a factor of 12. Since the determinant is positive, it preserves the orientation. Definitely because determinant of A is 12, that means it preserves the orientation. What would have happened if the determinant would have negative? Well, I am not going into this part. Here T is rotated, the cube is stretched and into a parallelepiped. The volume of this new parallelepiped, which is right on the right hand side of the screen, which is marked by x prime, y prime and z prime coordinate, has an increased volume. And the volume increases up to 12. So I think that I made it a clear part from 1 dimension to 2 dimension and 3 dimension how the volume under linear transformation changes. So let us summarize before we move on to the next part of the video. So the transformation's determinant specifies how the volume of the object changes. This is important. If the determinant is 1, the volume is preserved. If it is negative, there is a mirroring, which includes a reverse phase order, which we have not covered. You can look into any linear transformation book. When orthogonal transformations are applied, what are those orthogonal means? Rotation, translation, scaling, and then the shape is preserved. Now when the shape is preserved, when the orthogonal transformation happens, here what happens? This is a cube which has transformed into a cuboid. You can see I have marked it in red. The length part of the cube now has increased in the cuboid. The sphere become an oblate spheroid. So you can see that the blue part now has become much bigger. So this is actually what is happening during orthogonal transformations. Taken all these things together with an arrow, if V equals to 0, for example the volume, then the change after changing that part, what happens? It becomes V0 times X absolute value multiplied by the Y sub absolute value and the Z absolute value. This I have definitely taken for cube and cuboid. For the formula for a spheroid or an oblate spherical structure or an oblate spheroid would be something different. So this is what is volume transformation under linear transformation, how volume changes. This was important. You will soon understand the reason. To notice all those things which is right on the top of the screen. All these changes, like the 1D, then the flipping of the parallelogram into 2 dimension, then the cube over the cube, becoming a parallelepiped, increasing the determinant by 12. All these were on orthonormal basis. But because general theory of relativity deals with non-orthonormal basis, and rather I would say any kind of an arbitrary system, so this particular system of linear transformation would not work at all, because general theory, as I have discussed in the earlier video, doesn't even deal with any coordinate system. It just takes any arbitrary value. So here we have to introduce a new concept which is called volume element or volume form, which is denoted by this small omega sign. So here is a definition. The volume form is a special differential form defined on oriented Riemannian manifolds and which introduces a natural concept of measure on the manifold. It is a tensor. Well, what I would like to tell you, barring apart those technical terms, you can understand that the volume form or the volume element is indeed a calculation of a volume, but it is not on an orthonormal basis. It is a non-orthonormal basis, especially on a differential manifold where anything can take any shape. And the good news is that it is a tensor. So it has got a lot of information within it and it is preserved. So let us see what actually volume element means. So here is a cuboid. So in general we mean volume equals to length multiplied by breadth multiplied by height. Now if I take a volume integral, just a general integral of these 3 volumes, so what I can do is that I can do a triple integral over a surface region. It can be g of dx, dy and dz. So this is called the volume integral. Now you see the volume element. It is the differential element of dv, okay, that is the differential volume, whose volume integral over some range, any given range in a coordinate system, gives the volume of a solid, which is v equals to the triple integral of dx, dy and dz. So now you see from volume element we go to volume integral to volume. So this part is clear. So I hope I have been able to give you a clear definition of what different volume element of volume form is. So you understand that volume element is actually a differential element where we are taking the differential volume, we are triple integrating it with the three vertices x, y and z, and this gives the volume for or volume element. Okay, so volume element provides means for integrating a function. So here in a Euclidean space, you can see this is a cube, and the volume element is given by the differential of x, y and z, which gives the differential volume. Now in a spherical coordinate system, the volume element is given by this, which is on the left hand side corner of the screen. The differential volume equals to the square of the radius times sine theta, d theta, d phi and dr. So what I'm trying to show you actually is that this volume element form, how it is applicable from Euclidean space to spherical as well as to polar coordinate. So this is something that when we are trying to calculate the differential volume in different coordinate system, this volume element is very important, because you see, barring the Euclidean space, in spherical and in polar coordinate system, nothing is orthonormal. So it is given by this part, which is the sine u differential of u1, u2 and u3. Now I would like to give you a basic illustrative example of volume form. So here is a parallelogram, okay. So this would be given by the volume, this is A and B, these are the two vectors. So this would be given by the volume form omega acting on the vectors, which is A and B. Similarly, the volume of this cube is given by omega times A, B, C, which are the three vectors which are occurring in those. Now say we have two vectors A and B right here, and written in terms of our, if you have seen my earlier video, you would know what is E1 prime tilde and E2 prime tilde. These are basically, which is not orthonormal, which you can see that these two are not orthonormal. So how we do is that we get the volume. So first the square root of the determinant, which you can see I have written it as determinant of G. This is the square root of the determinant of the metric tensor. Now let us take a pause. Now try to understand what actually it means. So you have seen the previous example that in general we try to calculate the volume using a determinant. This is actually the same, but we take a square root. I'm not going into further I would say complications of the calculation. So understand it is the square root of the determinant, but determinant of whom? It is not of the parallelepiped, or it is not of the cube, because we are working on an orthonormal basis where we are considering metric tensor as the measurement, right? So determinant of G is actually what we get, the square root of the determinant of the metric tensor. This takes care, the determinant of G as I marked here, you see, this takes care of the transformation from orthonormal to non-orthonormal. And here you see on the bottom of the screen, W, this determinant of G, equals the square root of determinant of the metric tensor dot the determinant of this one, epsilon, it is called the Levi-Civita symbol. Don't worry, you can just ignore it. It is basically a easier way to write down the tensor part. I can make a later video on the significance of Levi-Civita symbol, but you can just consider for the time being that is the epsilon is the Levi-Civita symbol of ij components times B, which is the orthonormal vector B, its I component, and A, its J component. So this actually takes care of the volume change from the orthonormal to the non-orthonormal basis. transform on a non-orthonormal basis. Now this V actually denotes the volume, which is given by this omega sign, and this is written freshly. So this volume form is on the orthonormal basis. This is the non-orthonormal which you have seen just before, and it is combined with the Levi-Civita symbol with the three dimensions which I have shown earlier is ij. Now I'm considering the cube, so it would be ijk, c times c prime of ith element, a jth element, and b kth element. So from this cube, which is an orthonormal basis which we are trying to move to a not on orthonormal basis, this part becomes much more clearer. So the determinant of the metric tensor square root actually takes care of the volume change from the orthonormal to non-orthonormal basis. So just in order to avoid further derivations, if we come to what is called a Ricci tensor, you will see that Ricci tensor actually measures the change of volume along the geodesics, and this V minus sign actually denotes that this curvature is positive, and these two V which I have marked in purple is actually the volume. So you see here from orthonormal basis, which is the cube right on the top of the screen, coming to a non-orthonormal basis where we are taking the root over of the determinant of the metric tensor, which actually this V relates in further calculations, which we come to the actual formula of Ricci tensor, which you see right at the bottom of the screen. This V actually shows this V, which is the non-orthonormal basis V. And because V means volume, and because Levi-Civita symbol combined with the square root of the determinant of the metric tensor deals with the volume, so we can draw a conclusion that Ricci tensor actually deals with the change of volume along the geodesics. And this negative minus R denotes that the curvature is positive. Things will become much clearer as we proceed. What do we mean by the negative R? Now here is a sphere, and we see these two people are moving along the line and the geodesics, and eventually they meet on the North Pole. If you take a similar kind of a sphere here, and I mark those in red, this is what I called minus R. Okay, so this geodesic movement along the sphere. Now, for example, if I take a ball right here, right, and then here, and then here, and then here, and then finally here. So you see that the ball grows smaller, right? So this means that the volume moving along a sphere will always shrink as the geodesics, you can see, are always converging, right? The Riemannian curvature is always positive. Or sorry, I'm so sorry. The Ricci curvature is always positive. So in General Theory of Relativity, okay, let me show this one. So you see this is right at the bottom, you see the original Einstein field equation. This R mu nu is actually the Ricci curvature, right? And the Ricci curvature is always positive. So in general theory, you can see that gravitation and attraction is just the natural tendency of how space and time is curved, or I can say how space-time is curved. It doesn't require any additional force, right, as we used to do in Newtonian gravity. But this R, which is the positive, I would say the riccicurvaturetensor, which is positive, is actually making the ball grow small in size. Now you might be wondering, in the previous I told about minus R, here I am showing a positive R. Well, don't worry, that was basically a derivation. But that derivation actually means that negative R shows the converging of geodesics. So here on the right hand side I have written the ball shrinks in size as it moves along the geodesic. It means it is a positive curvature. Now if I consider the change in volume, how it happens, say for example this cube, I move it this way, so there is no change in volume, right? Why? Because it is a straight geodesic, right? If I consider the V1, V2 and V3, these are the three components of the Ricci tensor, considering the cube, it is 0. That means there is no change. If I consider the converged geodesics, which we have just seen previously on a sphere, this cube will shrink to this, right? So you see that cube, which is originally started on the left hand side, it reduces to a size of 1/4, and here Ricci curvature is greater than 0. Why? Because it is a converging geodesic and it is a positive curvature. If I consider something like this, these two are diverging. So the diverging geodesics, it will grow and grow and grow. So here you see it increases what it is there to approximately size of 1/4. So here the Ricci curvature, if I consider the components v1, v2 and v3 again, is less than 0. So here these are the straight away three comparisons of change in volume or the movement of matter according to geodesic. So in the Euclidean space, Ricci curvature is 0, so there is no change in volume. In the spherical, in the converging geodesics, the curvature, the volume shrinks. Ricci curvature is positive, greater than 0, and in diverging geodesics, we get Ricci curvature is less than 0, so the volume increases. So now I hope you can understand why I went back into linear transformation. I went back to linear transformation because in order to give you a basic idea that we are already encountering change in volume when we are moving from cube to cuboid, or when we are doing a linear transformation on second and third three dimensions. But combined with that linear transformation, when we do it in orthogonal plane, and then with all those calculations that we showed, actually leads to the change in volume. So change in volume, well, it is a term which confuses somebody, that how movement changes volume. This is how it does. So Ricci scalar, if I consider this part, if I now from Ricci curvature tensor we moving into Ricci scalar. So if it keeps the track of how the size of a ball deviates from standard Euclidean space. So just note what is the difference. Ricci curvature tensor was actually showing that how the ball is changing, I mean to say the volume is decreasing or increasing. That is Ricci curvature. How the volume of a geodesic or a matter moving along the geodesic changes or grows or shrinks or remains static in volume. That is Ricci curvature tensor. But Ricci scalar actually shows how the ball deviates from standard Euclidean space. So let us see some examples. This one is in flat circle. So when once from the 3D we move into 2D, it becomes a disk, right? Here it is. If I try to place this particular disk on this sphere, the blue portion which is right on the right hand side, you will see that the area is more. Yes, this red arrow denotes. If I try to what I would say immerse this disk on a sphere, the area is more, right? So this is how what Ricci scalar mentions. So this disk, when it is put up on a sphere, how much it deviates from the standard Euclidean space. So here I have written that the area that fits on the sphere is more than what fits in the flat space. So let us see for an example. So we get a circle whose area is pi r squared. Now if I try to put this circle along this this black one, you see it stretches, it increases. It further increases as the sphere gets smaller, and it further increases to 2 pi r squared as the surface area further increases. So this is actually what Ricci scalar does. So if you're asking that what actually Ricci scalar means, Ricci scalar is actually this. So this circle taken from a flat Euclidean space is trying to fit around a sphere from pi r squared, it moves to 2 pi r squared. So the surface, it increases further. So as the circles become shorter, I mean to say the sphere becomes shorter, we can fit more area. Hence we can say that we can fit a huge, large amount of area in a small boundary covered in the sphere. So here are a few examples of the geodesic deviations. In the flat, you see I have drawn two lines. It is totally flat. r equals to 0, that means there is no increase in volume. Ricci scalar is 0. Now here it is something which is a sphere, so we have learned that in a sphere this curvature is positive, so r equals to 0, and the volume, actually what it moves, it decreases. And in this negative curvature, which can be a great example of a saddle, there are few examples I haven't mentioned over there, which are great curvatures of negative curvature, great topology of negative curvatures. Here the volume increases, as you see the dotted lines becomes more. So you can just take a note of this. This is a wonderful presentation, I would say. This is a perfect area in which the geodesic deviations from 0 to greater than 0 to less than 0, and how it happens. No increase in volume, flat space, sphere increases the volume, the volume decreases, and in saddle, or when the Ricci curvature is less than 0, the volume actually increases. So no increase, it decrease, and then further increase. So this is one what I'm trying to show you, that Ricci curvature in flat space is 0. When it goes on we are trying to fit this ball right on the top, so Ricci curvature is 0, so we get more area. And if you're trying to fit it in somewhere where the Ricci scalar is less than 0, I would say then r is equal to 0 from the Euclidean space to this, it actually is the less area. So on a sphere where the r is greater than 0, we get more area, where the r is less, we get less area. But here we are comparing all this in terms of circumference of the sphere or of the ball. So here is the final show. So we get here a nice equation, which I will just explain you. This one is actually the Ricci tensor. Okay, this shows equivalent to Riemann curvature tensor. As I told you that from Riemann to Ricci scalar, and Ricci curvature tensor to Ricci scalar, and this one we all know is a metric tensor, and this is the Riemann curvature tensor. But we have to note that this C and B, you will see, has been omitted. So the Ricci curvature tensor, if you move to the curvature part, you see that this C is a contraction of the first and the third index. So you see on the left hand side of the Ricci tensor, there is R, we have got A, we have got B, but we don't get the D part. So the first 1, 2, 3, yeah. So the C and the D has been omitted in the Ricci tensor part. So the Ricci tensor, that is why I've written, is the contraction of the Riemann tensor, the Riemann curvature tensor, which omits the first, that is the C and the D part. You see the first C and D is not there. So Ricci tensor and the Riemann curvature tensor, the metric and the Riemann and again the Riemann curvature tensor. So we are coming to end of a very intensive video, and it's a time that we should summarize things. So we have learned what is mu nu, right? This is the dimensions of space-time, 4 into 4. We have also learned that how we can reduce Einstein's 16 partial differential equations to 10, because some of them are symmetric. Einstein's tensor and its zero divergence property, because Einstein tensor is zero divergence, and we have seen the stress energy momentum tensor also zero divergence, how the left and right hand side actually maintains the law of conservation of energy and momentum. But again, we have to remember that zero divergence doesn't mean it is the conservation, it is actually the covariant divergence, which we are considering in the general theory of relativity. We have also learned the stress energy momentum tensor, the T mu nu, and how stress and energy and momentum actually contributes in the curvature of space-time. We have dealt also with the elements of stress energy momentum tensor. We also went back and looked into what is a change of volume under linear transformation. We also looked into what is called differential volume or volume element or volume form, and how it is related to linear transformation. We also looked into what is Ricci curvature tensor and its relation to Ricci scalar. So both Ricci curvature tensor and Ricci scalar are basically, I would say, the Ricci curvature tensor, which actually shows the change in volume, where a Ricci scalar measures the deviation of a Euclidean ball when it fits on a spherical surface on a non-Euclidean place. Well, I think that it has been quite a long video, but I have to make it because these things were important in Einstein's field equation. Also, I understand that the metric tensor is being omitted. I am making my next video, which would be exclusively on metric tensor, because the video has spanned quite long and I don't know how well you have enjoyed, but I am going to take care of the metric tensor in the next part. Well, thank you for watching Physics for Students. Please do like, subscribe, comment, and please share your views. I'm always very thankful to those people who subscribe and comment. I have already extended my thanks and gratitude to all the viewers who are watching my channel. I am thinking of maybe, I'm not sure, to launch some new series on linear algebra, maybe on calculus, as well as on general topology, which is quite a demanding subject in this new arena. I would request you can put up your comments and please share among your friends, because Physics for Students, like, we take a lot of pain in developing these type of videos. So my next video, which is coming up, continuing with Einstein's field equation, will be metric tensor. So once we complete the metric tensor and we need to look forward what else are left, then we can combine all those components and we can make another video where we can explain these components finally on Einstein's field equations. Well, thank you very much for watching this video. Do subscribe, like and comment. Stay safe, stay happy, and watch out Physics for Students for a lot of new videos and new ideas which we are coming up. I would leave now, and I would leave with this wonderful soft piece of music for you all to enjoy. Thank you very much and have a good day.